So for most of the conversation, we'll focus on IB, but we just wanted to ask some more general questions about you and about your background before we jumped into the nitty-gritty details. So can you just describe your background briefly? Like, what were you doing before working on alignment, and what got you interested in alignment?
Well, it's a kind of it's a kind of long and a little complicated story, but well, to put it briefly, before working on alignment, I was working in the software industry, doing algorithm engineering, um, mostly in computer vision, some cybersecurity too, and yeah, and I was doing that for like maybe 15 years or something like that. Um, what got me interested is, well, it was almost accidental, just someone online linked a paper which seemed interesting. One thing led to another, and then I found less wrong and read about the alignment problem less wrong again. Gradually, I became convinced that it's something not only interesting but also very important. Yeah, that's how it began.
Okay, great. We were also wondering if you could talk about which individuals have had the greatest influence on you professionally, or and either with alignment or in the software engineering capacity.
Oh, which individuals influenced me professionally? It's a difficult question, because I usually don't think in those terms exactly. I kind of just absorb things coming in from all sorts of directions. And yeah, I mean, obviously reading the sequences, Eliezer Yudkowsky's sequences influenced me a lot, but there was like a lot of stuff. So it's not, it's hard to point out like one or two individual and say, yeah, they influenced me. It's like, yeah, I like, I think that in my youth, when I was studying a bunch of higher mathematics, I was influenced a lot by Joseph Bernstein, who is a mathematics professor in Tel Aviv University, doing like algebraic geometry and representation theory mostly. The fields are completely unrelated to alignment. Of course, that was many years before I discovered, the whole field of alignment. But I do feel like he influenced a lot the way I think about mathematics. So, in that sense, yeah.
Are there any ideas about alignment that have popped up in the field recently, like whether they're your own ideas or whether they're someone else's ideas that you're especially excited about?
Well, I mean, well, first of all, yeah, I'm certainly excited about my own ideas. That's why I'm working on them. Especially the concept of what I've been calling PRADCA, like a new approach to how to use infra-Bayesian physicalism to design alignment protocols. So that's something I'm really excited about recently. But yeah, but I also find I certainly find Paul Christiano's work very interesting. So he's kind of thinking about these questions very informally, which is on the one hand unsatisfactory from my perspective. On the other hand, he does generate a lot of ideas, which I find useful, and which definitely entered my thinking about the problem. Yeah. So I guess that, and John Wentworth's research is also, I think, fairly interesting, but I'm still not sure exactly where is it going. But it might be going to some really interesting place. But I'm just kind of not exactly sure.
Okay, yeah, that makes sense. We're also interested in pre-DCA, and we'll hopefully have time to talk about it later on. We were also wondering if you had any advice for people who are relatively new to alignment on like how they could contribute or what problems they should be looking at, or like how to frame different like research directions, etc.
Well, I mean, there are, as you know, there are different approaches which are very different. Like some people are doing empirical research, some people are trying to make interpretability tools. I'm personally interested in the side of creating mathematical theory, but I also think that this is genuinely, well, the most neglected, at least, area. It feels to me like the most neglected area, because there's a number of groups doing empirical research and a number of groups doing interpretability. But when it comes to theoretical mathematical research, what Paul is doing is also kind of theoretical, but he's not really using a lot of mathematical formulas. There are really not many people. I mean, Miri were kind of leading the effort in that direction, but recently they, kind of pivoted, and they're kind of pessimistic about the ability to solve the problem from this direction in time. And I'm more optimistic. I'm not like, I'm also overall rather pessimistic about the situation, but I think not quite as pessimistic as Yitkowsky, for example. And so I feel that the theoretical mathematical research is something where we're really missing, and we could use more researchers. So yeah, I think that people who are capable of working the problem from this angle, I think they should be doing that.
As you've been pointing at more than most other researchers, you really emphasize that our eventual solution to the alignment problem should be based on a really sound mathematical foundation. And so, yeah, why, in your view, is mathematical rigor so important for alignment? And what are the main arguments that other people might give that we can be a bit looser?
Yeah, so there are a number of reasons, or like maybe a number of ways to look at it. At like why mathematical rigor is so important. One way to think about it is that, or like one reason is that mathematical theory gives us a vocabulary to talk about the problem, right? Like, for example, if I make an analogy with like thermodynamics and building engines, right? Or like building like machines, then thermodynamics gives us a lot of concepts like energy, entropy, heat transfer, so on and so forth. Without having this vocabulary, even when you're discussing something informal, when you're not actually like making calculations or proofs, even when you're just thinking about the problem, just having those concepts is really important to make your thinking a lot clearer on the topic. And like to have this vocabulary to understand what the correct concepts are, having mathematical theory is crucial, because like, how would we be able to talk about entropy in thermodynamics if there was no mathematical theory behind it? So this is like one reason. Another reason is that, of course, we want to be able to actually prove that our safety protocols actually work, that they are actually safe. And of course, when when I say proof, any proof uses some assumption, like any model has some assumptions, but this is still an enormous advantage, being able to reduce your confidence, like your claim that this protocol is safe, to some crisp, well-defined assumptions that these are the assumptions that I'm basing it on. And then hopefully those assumptions can be tested empirically, can be maybe inferred from other sciences and so on and so forth. But it gives you a huge, it gives you an extremely powerful tool to be confident about those things. And when you are aiming at a small target, like you think we are in alignment, then we need to have those powerful tools in order to be able to hit this target. And I would say that the third reason why mathematical formalism is important is because if we're relying purely on empirical research, then without an underlying theory, we don't really know how to extrapolate from the research we have. Like we did some experiments, but we got some results, but what does it mean for other architectures? What does it mean for other data sets? What does it mean when we scale our compute? Okay, suppose we observe some trends, but are those trends going to continue indefinitely, or are there some phase transitions? We don't know. We're just like in the dark without like a theory to back all this up.
Can you expand a little bit more on what this mathematical theory, what you imagine or expect that it will look like? Like, what is it a mathematical theory of? Like, is it a mathematical theory of intelligence or of human values or both? Why do you expect that a mathematical theory of intelligence exists and is out there and is able to be found? Yeah, can you just expand a little bit about on what this mathematical theory might look like and what it's a mathematical theory of?
Yeah, so when I'm talking about a mathematical theory, I'm talking about a mathematical theory of intelligent agents in general. It's definitely not going to be specific to humans or to human values. Human values are expected to be very complex, and human minds are going to have they have a lot of random features that made their way into those algorithms by evolutionary accident. And of course, they're not going to flow out some simple mathematical theory. The mathematical theory should be on the level of abstraction where we're talking about intelligent agents in general. Why do I expect such a theory to exist? That's a good question. And I think there are like multiple lines of reasoning that lead to this conclusion. So one line of reasoning is that in general, I expect simple mathematical theories to exist when we're asking questions that are natural in some sense. So to give an example, if we're asking, what are the fundamental laws of physics governing the universe? That's a pretty natural question because this question doesn't have any parameters in it. Like there's one universe. Okay, maybe you can argue whether there's one universe, but still, so first approximation, there's one universe and it has certain laws of physics and that's all. Like, so on the other hand, so you can expect those laws of physics to be simple. On the other hand, if you're asking something like, what's the shape of the continent of Africa? Then it would be ridiculous to expect a simple mathematical formula for this shape, because this is just one continent and one planet out of, a zillion of planets out there in the universe that all have all sorts of random shapes. So this is a question which comes with some very, very, a lot of complexity hidden in the question of self, like specifying what is Africa out of all possible continents, all possible planets already hides a lot of complexity. So I see it as a kind of law which says the amount of complexity going in should be the amount of complexity going out. If you're asking a very complicated, very specific question, then you should expect a complicated answer, and vice versa. And I think that with intelligence, we are asking a question which is simple or natural. Why? Because in some sense, well, one way to think about it is a theory of intelligence, but another way to think about it is that it's just a theory of metaphysics, right? Like, intelligence is an algorithm that is trying to take observations and make inferences about what the world looks like. So this, in some sense, is the most fundamental thing out there. It's more fundamental even than the laws of physics, because the way we derive the laws of physics is by applying some principles of metaphysics, which today have not been formalized. But this is just kind of the flip side of the same coin. You can call it the mathematical theory of intelligent agents, but you can also call it the mathematical theory of metaphysics. So this is kind of the simplicity argument. It's kind of a philosophical argument why we should expect this theory to exist. But another argument why we should expect this theory to exist is just because it already kind of exists. Like, we don't have the whole theory, but we are already uncovering parts of this theory. And I feel like it looks like it's there, right? We don't have, you know, the whole ship is not out there, but parts of it are already poking out of the ground from which we're digging it out. And it seems like it's there.
Yeah, well, one solid, more or less solid start on a formal mathematical theory of intelligence is ICSI, which in a nutshell is just the perfect Bayesian reasoning using the Solomonoff prior. But ICSI has quite a few flaws, and one of those flaws is that it performs really poorly in non-realizable settings. So can you describe what non-realizability is?
Yeah, so realizability. So the distinction between realizable and non-realizable is it comes from statistical learning theory. And in statistical learning theory, we are talking about having some phenomenon which we are trying to learn, trying to model. And there is some class of hypotheses which we're using to describe this phenomenon. So our learning algorithm is taking in data and outputting some hypothesis from some class. And the realizable setting is when there is a particular hypothesis in the class, which is an exact description of the physical phenomenon. The non-realizable setting is everything else, when we don't have this exact description. So in realistic problems, you should always expect things to be non-realizable, because the world is very complex. So if you're dealing with an actual physical phenomenon rather than, you know, some toy model or just some simple computer simulation or something like that, then because of the complexity, the computational complexity of the physical world, you can never expect that any of your hypotheses will be an exact description. And in statistical learning theory, there's a lot of theory of like what happens in the realizable setting, what happens in the non-realizable setting, but one missing piece there is that for reinforcement learning, we only have good theory, or we only had good theory in the realizable case. And of course, AIXI is basically a special case of reinforcement learning, basically reinforcement learning with some specific prior. So what basically it means that if you're just thinking, you know, for example, you can say, oh, I'll just solve everything using Bayesianism. But when you're doing Bayesianism, an interesting thing happens is when you're in the realizable case, so the environment is actually inside your prior, there are theorems which show that you're guaranteed to converge to the correct hypothesis. But when you're in the non-realizable thing, then in general, nothing can be guaranteed. So sometimes you can guarantee something if you make some ergodicity assumptions, but those are also some very strong assumptions that you cannot, that you don't have in general.
So how important, for the purposes of alignment, how central do you see the non-realizability problem? Like how central of a roadblock is non-realizability to making progress towards a mathematical theory of intelligence that we can use for alignment? Like is non-realizability one of the central roadblocks, or is it more peripheral? Where would you place it?
Well, it's certainly one of the roadblocks, and I think a pretty central one, because non-realizability, it's connected to a lot of other things. Like when you're thinking, for example, of systems that are self-improving, then you immediately run into non-realizability, because like you have this paradox that the system cannot have a perfect model of itself. When you're thinking about multiple agents interacting with each other, you run into non-realizability, because it's not possible that each agent can stimulate the other agent. You also get some kind of a paradoxical loop. When you're thinking of Newcombian paradoxes, then of course you also get non-realizability, because this omega in the Newcombian paradox is non-realizable. When you're thinking of embedded agency, you have non-realizability, because if the agent is part of the physical universe, then the physical universe is bigger than the agent, so it cannot possibly fit into the agent's hypothesis. But so this is kind of something that's popping all over the place, and if you don't know what to do about it, then there's like a whole range of questions that you can't even begin to answer.
And to get around the problem of non-realizability, you and Diffractor came up with, you took some concepts from imprecise probability theory and modified them, and then applied them to the theory of reinforcement learning. And you called this kind of a meshing of imprecise probability theory and reinforcement learning theory, infra-Bayesianism. So can you just describe what infra-Bayesianism is and how it helps us get less confused about non-realizability?
Yes. So imprecise probability theory is something that comes from decision theory and economics. And the idea there is, instead of like the usual kind of Bayesian probability theory approach, where we just always formulate our beliefs as probability distributions, in imprecise probability theory, we have some more general objects where probability distributions are just a special case. And this, well, one example of that is so-called creedal sets. So instead of having just one probability distribution, you have a convex set of probability distributions. And then if you need to make some decisions, then you're taking the action that maximizes the minimal expected utility over this convex set. So that's like the maximum decision rule. So what we did is we said, okay, so why not, so let's take reinforcement learning theory, but instead of every hypothesis in a hypothesis class being just a normal probabilistic hypothesis, let's make it an imprecise probabilistic hypothesis, right? Let's just kind of generalize the notion of environment. It's using reinforcement learning. Let's generalize it to imprecise probability theory. And that turns out to work pretty great. Although even just defining exactly what an environment is, you find a lot of interesting mathematical nuances. And then we can talk about the usual kind of concepts we have in reinforcement learning theory, like, for example, regret bounds, and start proving regret bounds about those infra-Bayesian reinforcement learning. Or one thing we worked on is the updating rule. Like, what's the analogous thing to the updating rule in Bayesian theory? We constructed a certain infra-Bayesian analog to that, which required us doing more generalization beyond what's usually used in imprecise probability theory. Yeah, and then we kind of saw that you can take this framework and apply it to Newcombian paradoxes, for example, and get some very nice way to solve them and apply them to all embedded agency and all sorts of things.
One question that I have is, and that I imagine that a lot of other people have, is the goal to come up with an understanding of the way that we expect AGI to reason, the most likely decision rule that AGI will use, or are we working on infra-Bayesianism because we'd like to somehow force the AGI to have a specific decision theory, to follow a specific decision rule? Does that question make sense?
Yeah, that's a good question. So that's like asking, do we want a descriptive theory or a prescriptive theory, right? And we kind of want both. Like, it's getting a little into the woods of, like, what AGI is. So, like, one thing we want to do is to have a mathematical definition of what does it even mean to have AGI. And one line of reasoning would be an AGI has to be doing something like infra-Bayesianism, because one of our, like, if we define AGI as something which is the reason that's sufficiently sophisticated to be able to operate rationally in non-realizable setting, then it should be doing something. Like, for example, we can hypothesize that such a reasoner should be doing something akin to infra-Bayesianism. Yeah, and in that case, we're kind of thinking, from that angle, we're kind of thinking of infra-Bayesianism not as like a recipe for how the algorithm looks like necessarily, but more like a desideratum. Like, we think that something is an AGI if, for example, it satisfies some sufficiently good regret bound with respect to some sufficiently good infra-Bayesian product. Like, that's one way how you could try to define what AGI is. But you could also take it to the prescriptive angle of, like, well, if we want to construct AGI and we don't want to just do trial error until we find out something that works, then how can we think about it? So obviously infra-Bayesianism is not a particular algorithm, but it could be like a guiding principle to what type of algorithms you can kind of imagine being relevant. Yeah, there's also an interesting question of, okay, but what happens if we take some really good algorithms, but we're building something which is like specifically designed not to be infra-Bayesian? Like, we're just designing it to be a Bayesian all the way, just purest Bayesianism. But other than that, we're doing some, the best possible algorithms for everything. Is this thing AGI? Is this thing not AGI? And this is an interesting question. And I have kind of an informal conjecture currently, which is that if you're doing something of that sort, like you're building some powerful algorithm for some definition of powerful, but it has some of those kind of conceptual ingredient missing, like infra-Bayesianism or other things, then this is probably going to imply that you're going to have an inner alignment problem. That your agent is going to develop a sub-agent on its own that is going to be infra-Bayesian and infra-Bayesian physicalism. But the sub-agent is probably going to have some completely different reward function. So, it kind of like evolution produces human brains, or like evolution is a very unsophisticated learning algorithm, whereas human brains are a much more sophisticated learning algorithm. But like in the transition, you kind of switch to a different, to a very different reward function. And like that's basically the inner alignment problem. So the informal conjecture is kind of saying that the thing that, you know, the definition of AGI that this whole line of reasoning is leading to is going to be some kind of a attractor in the space of sufficiently advanced cognitive systems, or something like that. So like even if your system didn't start out as something with those properties, so we'll end up with something with those properties.
How confident are you that Informationism will end up being a significant factor in helping us solve alignment?
Yeah, that's an interesting question. Like, I feel that on my inside view, I am relatively confident. Like on my inside view, I feel fairly confident. But I also feel that you know, the kind of beliefs, all things considered, should not put too high weight on this inside view. So I don't know if I want to really put a number on it. I feel like there's a considerable probability that infra-Bayesianism is going to be crucial. There is also a probability that we'll discover that somehow this line of reasoning was at that end and that there's something else. So I don't think that there's a negligible probability of either thing, but overall I'm pretty optimistic about infra-Bayesianism being a useful ingredient, and kind of definitely pessimistic about solving the alignment without solving the problems that infra-Bayesianism is trying to solve. Quite pessimistic about that. And, you know, I'm kind of inclined to think that infra-Bayesianism is the correct solution, but I can't say that I know this with 100% certainty or something like that.
Okay, yeah. So we've talked a bit about infra-Bayesianism. I was wondering if we could talk to you about one of its applications, infra-Bayesian physicalism. So I was just wondering if you could speak about what problem infra-Bayesian physicalism is aiming to address.
Yeah, so infra-Bayesian physicalism is kind of an approach to the problem of embedded agency, or maybe more correct to say some aspects of the problem of embedded agency. And, one way I like to formulate this problem is, I'm calling it the problem of privilege. So why the problem of privilege? Because all the classical, like the way we classically think about, for example, reinforcement learning, what I call the classical cybernetic framework, where you have an agent that is taking actions and making observations, everything is formulated from the perspective of the agent, from the point of view of the agent. So the agent is kind of a privilege, regarded as a privilege point inside the universe. That's why I'm calling it the problem of privilege. And that's very different from how we reason when we're doing, for example, when we're doing science. When we're doing physics, we don't expect the laws of physics to have humans as somehow important variables inside the equation. The laws of physics, we expect them to be described by simple equations where the variables in those equations are some kind of fundamental degrees of freedom, some kind of quantum fields or whatever, strings, whatever, which have, which are very remote from agents or humans or whatever. And this difference is really, really important because, for example, in the AIXI model, we rank hypotheses by their description complexity. But this is the description complexity from the subjective point of view, not from the objective point of view. So on the one hand, the motivation for this Solomon of prior is Occam's razor. On the other hand, the way we use Occam's razor in AIXI is very different from how we use Occam's razor in science because of this difference between the objective and subjective point of view. And this difference actually corresponds to some huge penalty in the description complexity, because the translation between those 2 points of view, the translation from quantum fields, for example, to, I don't know, pixels on the camera of your robot, or like the photons in your eye or whatever, is very, very, very complex. And this, you can show that this leads to a whole host of problems. And this shows, well, some of those problems are actually alignment problems, like a causal attack problem pointed out by Paul Cristiano. And this is, by the way, a wonderful example of something I mentioned in the beginning of the universe, that Paul Cristiano, even though he works informally most of the time, he generates amazing ideas. And for example, this causal attack, this notion that the Solomon of prior is malign is a very, very important observation, I think. So some of the problems are alignment problems, but some of the problems are just just showing us that the AIXI model is not really doing something sensible. And this is the problem that information physicalism is trying to solve.
Okay, could you speak briefly about how information physicalism aims to approach this problem, or like what update to like an infra-Bayesian agent, an information physicalist would have that would allow it to account for this?
Mm-hmm. So in infra-Bayesian physicalism, what we do is precisely switch from this kind of privileged subjective point of view to a bird's eye view. So instead of describing our hypothesis about the universe in terms of actions and observations, we're just describing them as there's some ontology, some notion of states of the physical universe, and there's also facts about computations, which we kind of operationalize as mappings from programs to outputs. So you can like talk about facts like 2 + 2 = 4. And an infra-Bayesian physicalist hypothesis is a joint belief about the product space of this physical ontology and the space of mappings from programs to outputs. So in other words, a physicalist hypothesis is a hypothesis which is a joint belief about what the physical state of the universe is and what is true about computations. And importantly, the ontology of the physical universe here is arbitrary. It can be different from hypothesis to hypothesis. It's not tied to anything. And the notion of belief we use, of course, is the notion we get from infra-Bayesians, or some particular variant of infra-Bayesians. And then the tricky part is, okay, but in the end, we have an agent that's supposed to take actions according to observations it sees. So how do we connect those 2 points of view, the objective bird's eye and the subjective point of view? And here is the interesting part, because we found that there's a mathematical object that we call the bridge transform, which allows us to connect those points of view, and it has all sorts of nice mathematical properties. So yeah, so basically all comes together nicely, and you can actually define what it means for an agent to be like choosing its policy according to a prior over those physicalist hypotheses instead of a prior over subjective hypothesis.
Could you speak a bit more about how the bridge transform is actually done, how we relate like observations and actions which are in this subjective point of view to our hypotheses, which are in this sort of objective or bird's eye viewpoint?
Yeah, so the way the bridge transform works is, well, the important observation is that you need to take a philosophical computationalist point of view. So the point of view that we think is that the important thing, in some sense, is which computation the universe is executing. And, this is not trivial that this is a concept that you can define, but the whole point of this framework is that we get to define it. So the way it works is you can take some program and given a certain joint belief about physics and computation, because it's a joint belief, it allows for some entanglement between computations and a physical state. You could have a situation where when you consider counterfactuals, like in infra-Bayesianism, you have a notion of counterfactuals. When you consider counterfactuals, so what happens if this program produces such output, whereas what happens if this program produces a different output, it can happen that the physical state of the universe is going to look different, or not. Maybe it's going to look the same. And then we're going to say that if it looks different, then it means that the universe is actually running this program. If it looks the same, then the universe is not running this program. So this is the kind of basic idea, but then there's a bunch of work you need to do to get from this to an actual mathematical definition. But turns out that you can do it. And then what this buys you is that you end up with the belief about computation, physical states, and which computations are running. More precisely, it's something more complicated than which computations are running. It's like more so like which information about computation does the physical universe have? But the first approximation, you can just think about it as like which computations are running. And then when you have this thing, then this already allows you to start to connect it to the subjective point of view. Why? Because then you can also consider counterfactuals of the form, okay, I'm an agent, I'm a particular program, I'm also a program, and I can consider counterfactuals which are of the form, what if I follow this policy, or what if I follow some other policy? So these are just counterfactuals about programs, because I'm a program. And now you can apply those counterfactuals to the result of the bridge transform and see what happens to which programs are running and which programs are not running. And this thing, on the other hand, you can interpret as things that you're observing, for example, because the fact that you're making some observation, you can operationalize it as, you making an observation. It means that the program, which is you, is running on an input, which is this observation that you make. So you see that it all comes together and kind of the subjective point of view gets, it gets a concrete mathematical meaning within this kind of objective framework.
Yeah, thank you. That makes sense. You mentioned that we can decide between different policies using this like counterfactual idea. What criteria are we using to decide between policies? I imagine it's some sort of loss function, but how is that defined in physicalism?
Yeah, so to decide on a policy, well, it's basically, like always, you want to minimize the expected loss. The only, the tricky part is what is lost and what is expected. So what is expected is in some sense solved by just regular information, because we have information beliefs and there's a notion of taking expected values. But the loss function here is interesting because the loss function is defined on the space of what is true about computations and which computations are running. So the thing your agent actually cares about is, kind of mathematical facts or facts about which computations are running in the universe. And this means that this kind of agent, it kind of has a philosophical commitment to computationalism. So in other words, it does not distinguish between a thing and a simulation of a thing. But anything that you can define as a computation, you can operationalize as a loss function for this type of agent. For example, if you want your agent to make a lot of paper clips, then you need to come up with some physical models in which you can define the concept of a paper clip, and then have this agent optimize how many computations which are simulating this physical model are running, such that within the simulation there is a large number of paper clips. That's like how you would make a paperclip maximizer in Physicalism.
Yeah, that makes sense. In the original sequence on Physicalism, you mentioned that loss functions have to obey the monotonicity principle. I was just wondering if you could speak about what that is and what loss functions would that property look like?
Yeah, the monotonicity principle is kind of the most controversial, problematic, and weird thing about this whole framework, because the monotonicity principle basically says that the loss function, it has to be monotonic in which programs are running, in the sense that if more programs are running, this can only be either the same or better. It can never be worse. And this is really weird if you're trying to implement something like human values, because it seems that for humans, there are sometimes programs that we don't want to run, like programs which simulate humans that are going through such terrible suffering that they would rather not exist at all. Maybe we have like a positive preference for this program not running, but that's like something that you cannot actually, well, something that's at least on the surface is not consistent with the Mentalistic principle. And and to be honest, I don't really know how to resolve this contradiction. I have like a series of different ideas how this contradiction might be solved, but I don't know what's the correct thing. Like, maybe it means that we should just accept that humans are not physicalist agents, and even if the AI is going to be physicalist, you need to, take into account that the humans are not physicalist. Maybe it means that we just need to generalize the framework. Maybe the framework is just not good enough as it is. There are some weirder solutions which sound really weird, but who knows? Like, for example, there's a line of argument which says that because the universe because there is a positive cosmological constant and the universe is asymptotically de Sitter, means that within our cosmological horizon, the number of computations it's actually possible to run is finite. So if there's just a finite number of computations that you can run, then having preferences for running something or for not running something, it kind of becomes almost the same thing, because a computation which is like suboptimal in its running, it's like taking the slots of some other better computation that could run instead. So like in a finite universe, maybe you can kind of operationalize this kind of preferences. And then you can continue to argue that, well, the fact that the universe is finite is also not a coincidence, because if you're a physicalist, you should kind of expect the universe to be finite. Because if the universe is infinite, then in many cases, well, not necessarily, but often it would lead to the universe running all possible computations. Because like in an infinite universe, a lot of things happen, and eventually somewhere, sometime, someone will run, do practically anything. And if all computations are running, then it's like it means that, and the only thing you care about is like which computations are running, then this whole hypothesis gets just assigned a constant utility number, which you cannot influence. So you might as well just forget about this hypothesis and like just throw it out. So like you could argue, and I admit that it sounds really weird, but again, who knows? You could argue that from physicalist point of view, you should expect the universe to be finite. And we actually scientifically, empirically know that the universe is finite. And once the universe is finite, this kind of problem of formalizing non-Montagne preferences seems like it's getting, seems like it's not such a big problem anymore. So that's like an example of one weird solution. But I admit that I don't know what's the right way to solve this.
Okay, thank you. That was well explained. Yeah, I guess we've got about 5 minutes left. It would be great if you could talk to us about pre-DCA and yeah, particularly like what steps are entailed in that process, as well as like I imagine it's a protocol for solving the alignment problem and how it seeks to approach both inner and outer alignment.
Yeah, so the idea with Bradka is that infra-Bayesian physicalism gives you a whole list of mathematical building blocks for formalizing concepts that hitherto were informal. So you can we already talked about the fact that you can formalize which programs are running, but you can also formalize which programs are agents. And you can probably formalize which utility functions or loss functions that these agents are optimizing. And you can also formalize counterfactuals. You mentioned that too. And that also leads you to formalizing causal relationships between agents. And once you have all of these building blocks, then it seems like it's a very powerful toolbox for specifying, what we actually want from our AI. And for example, what I'm doing in Bradka is I'm saying, okay, so we know which programs are running, we know which of them are agents, so we know which agents exist in the universe. Now we only need to decide, and we know what their loss functions are, so only remains to decide who of those agents is the user, and then we need to follow the user's utility function. And to decide who of those agents is the user, we use this notion of causal relationships between agents, and in some sense, the agents that closest to me, in the sense of like causal links, is the user, and that's basically it. Well, there's an interesting part there where the way we infer the utility function of the user is by looking only at its past and not in its future, like the computation that already ran, not the computation I'm going to run. And this kind of, in one fell swoop, solves us the big problem with value learning, where AIs get motivated to hack the input channel or get motivated to hack the user itself or something like that. So you don't have this kind of hacking problem. You also have much more information about values than in standard value learning, because in standard value learning, you're just using the observed actions the user took. And here you're using the computation that the user was running to produce this action, which gives you a lot more information. And it also seems like it has at least the potential to solve the inner alignment problem, because if we are able to prove that in any hypothesis that kind of survives the learning process, any such hypothesis contains the agent which is the user, then, well, basically it means that all those hypotheses are aligned in some sense. And like you could make an argument that like the usual arguments like this kind of simulation hypothesis that Paul Cristiano came up with, why inner alignment necessarily fails in like other frameworks. Here it seems like it doesn't work, because well, if you live in a simulation, the simulation still contains the user, at least if the fidelity of the simulation is good enough. And even if this fails, then we have other tricks to use the same toolbox to filter out hypotheses which we can infer that they are malign hypotheses. So the inner alignment problem seems like it's also becomes tractable using this toolbox.
Great. Well, I think that about wraps it up. Thanks so much for your time, and we're both really intrigued and inspired by the work that you're doing. So yeah, thanks. Keep getting your sleep and eating your vegetables. There aren't many researchers who are doing the kind of work that you're doing. So thanks very much.
Yeah, thanks a lot for the kind words.